8-year study of glucose A1C measurements among finger, CGM, and lab methods, No.1613, April 25, 2026. Gerald C. EclaireMD Foundation, Category Diabetes. Preface. Since my stroke on June 21, 2025, during the past 10 months, I have focused primarily on stroke, including its causes and consequences. During this period, I wrote approximately 280 papers. Only in the most recent 2 months did I begin to study one of the complications following my stroke, epilepsy seizures. I have written about 10,000 words of learning notes along with 3 papers on seizures. Compared to my stroke-related work, this is still a relatively small effort. Nevertheless, I have already drawn several important observational conclusions. Obesity remains the primary cause of type 2 diabetes, although a minority of patients develop diabetes due to genetic reasons despite being lean. The majority of diabetes cases originate from obesity. This condition develops slowly over a long period and is extremely difficult to reverse. Body weight control is one of the most challenging aspects of health management. For the purpose of this paper, I will temporarily set aside obesity and focus on diabetes as the second layer foundation of many metabolic disorders that eventually lead to mortality-related diseases. Approximately 85% of stroke cases are closely associated with metabolic disorders and are strongly influenced by diabetes. On the 11th of September 2025, from my own brain CT scans, I observed microvascular calcification, which I believe was caused by my 36 years of diabetes. This observation of microvascular calcification on my brain CT scan serves as a sobering reminder of the long-term silent damage caused by decades of diabetes. Even when recent numbers are under control. During the first 20 years after my diabetes diagnosis in 1990, I relied primarily on diabetes medication without any efforts on lifestyle changes, based on my viscoplastic energy model VMT. This period contributed approximately 91% of my cumulative metabolic damage, which ultimately led to my stroke. During the following 16 years, I discontinued medication and relied entirely on lifestyle management. This period contributed about 9%. Aging was excluded from this comparison since it exists in both periods. The resulting ratio of 91% to 9%, approximately 10 to 1, strongly suggests that medication alone cannot fundamentally control metabolic conditions. Whereas lifestyle management plays a dominant role, this 10 to 1 ratio also suggests that while medication manages the symptoms, lifestyle manages the viscoplastic energy or cumulative damage to the cerebral microvascular system. However, lifestyle management is far more difficult and complex than medical treatment. There is no single academic discipline in any college that fully integrates and teaches food nutrition, physical exercise, life behavior, psychology, and physiology as a unified system. In many ways, it is as complex as a full medical curriculum. Besides, the majority of people lack strong willpower and persistence to carry through fundamental and meaningful lifestyle modifications. Returning to the main topic, diabetes is strongly linked to major chronic diseases. Approximately 85% of strokes are related to diabetes. Approximately 75% of cardiovascular disease (CVD) is related to diabetes. Approximately 65% of chronic kidney disease (CKD) is related to diabetes. Approximately 15% to 45% of cancers and dementia are related to metabolic disorders. Globally, nearly 500 million people suffer from these 5 different types of mortality-related diseases. This represents approximately 6.25% of the global population of 8 billion. The impact of diabetes is broad, deep, and far-reaching. Therefore, this paper is dedicated to studying one central variable, glucose. To avoid the noise caused by differences between patients, I use single-patient longitudinal data. Each person has unique genetics, organ stiffness, insulin sensitivity, red blood cells (RBC), lifespan, lifestyle, and stress responses. Mixing many patients hides the real metabolic signal. By studying one body my own over thousands of days with consistent measurements, all structural factors stay stable. This allows the true dynamics of glucose and other pathophysiological behaviors to appear clearly, without statistical distortion. Introduction. The first question to address is the validity of glucose measurements. In this study, I analyzed 3 different methods of glucose assessment. 1 finger-piercing method, self-monitoring, approximately 4 measurements per day, to continuous glucose monitoring (CGM). Approximately 96 measurements per day. 3 laboratory HbA1c testing, conducted every 90 to 180 days. My CGM data collection began on August 1, 2018, following FDA approval in the United States. Initially, I tested both 5-minute and 15-minute sampling intervals. After about 1 year of comparison, I found that the difference between these two sampling frequencies was minimal, and I standardized my data collection at 15-minute intervals, 9 measurements per day. Over approximately 8 years, my dataset includes 7.76 years x 365 days x 100 measurements per day equals 282,300 glucose data. This represents a very large longitudinal dataset of glucose measurements over 2,823 days, the 1st of August 2018 through April 25, 2026. In addition, my quarterly laboratory-tested HbA1c data provide long-term validation. Although HbA1c reflects glycation of red blood cells or BC and differs in mechanism from direct glucose measurements, it serves as a widely accepted clinical reference. Before 2018, my diabetes condition was much more severe. Around 2010, my HbA1 reached 13%, and my glucose levels were approximately 360 mg DL. And fortunately, I did not have detailed continuous data during that period. Therefore, this study focuses on the stabilized phase beginning in 2018, when Libre CGM became available in the US. Few medical studies possess such a detailed, long-term, high-frequency dataset from a single individual. This dataset reflects not only persistence and discipline over 17 years, but also the ability to integrate mathematics, physics, and pathophysiology into a unified analytical framework. By the way, CGM is superior for behavioral learning, which aligns with my lifestyle-first philosophy. Section 1. Data comparison and observations. The comparison of the 3 glucose measurement methods reveals a clear and consistent pattern across the period from 2018 to 2026. All 3 A1C curves, finger-based estimation, CGM-derived A1C, and laboratory-tested A1C, follow the same overall trajectory: elevated levels during 201A to 201 linear letters. Declining trend during 2020 to 2023, a slight increase during 2024 to 2026. The timing of peaks and valleys is aligned across all 3 methods. This alignment indicates strong consistency among the datasets, based on statistical analysis. The correlation coefficient is approximately 0.90 to 0.91. With an RA value of approximately 0.84, this means that about 84% of the variation is shared among the 3 measurement systems. The remaining differences are relatively small and consistent. The typical deviation ranges from 0.2 to 0.5 A1C units, or approximately 3% to 7%. These differences are systematic rather than random, and likely arise from measurement methodology, rather than physiological inconsistency. Section 2. Interpretation of measurement differences. The observed differences between these 3 methods can be understood as measurement bias rather than true biological variation. Finger measurements provide discrete sampling of glucose values at 4 distinct time points: early morning fasting and 3-2 post-meal measurements. CGM provides dense 96 times per day continuous sampling. Laboratory A1C reflects an integrated biochemical process based on red blood cells or BC glycation. Despite these differences, all 3 methods are measuring the same underlying metabolic system. Therefore, they converge toward the same long-term average behavior. This convergence indicates that the body's glucose regulation, when stabilized, produces a consistent long-term signal that is robust across measurement techniques. Section 3. Sampling density versus long-term accuracy. A key finding of this study is that sampling density does not significantly affect long-term A1C trends once sufficient coverage is achieved. Finger prick measurements for times per day and CGM measurements 96 times per day both produce similar long-term A1C trajectories. This is because A1C represents a time-integrated average of glucose levels. From a physics perspective, glucose T represents a time-dependent signal. A1C represents the time-integrated average of that signal. A1C is approximately proportional to 1T asterisk integral of glucose T dt over a time period T. Describe these for finger measurements in an arithmetic form: G_finger equals G_fasting plus G_2 breakfast plus G_2 lunch plus G_2 dinner. For where G_fasting equals early morning fasting, glucose _2 hours breakfast equals 2 hour after breakfast _2 hours lunch equals 2 hour after lunch _2 dinner equals 2 hour after dinner. This expresses my idea clearly. Discrete sampling equals average of 4 specific time points. If I want a slightly more physics-style version, E_finger equals sum of GT_I10. Where N equals for increasing sampling frequency improves resolution but does not significantly alter the integrated average when the system is stable. Therefore, higher sampling density improves short-term visibility spikes. Variability, but does not significantly change long-term averages. Section 4. Clinical and practical implications. This finding has important implications for diabetes management. For long-term metabolic control, finger prick measurements are sufficient to estimate A1C trends. For short-term dynamics, CGM provides critical insight into glucose variability, spikes, and post-meal responses. However, average CGM A1C is about 4% higher than average finger A1C. CGM a finger equals 6.68, 6.42 equals 1.0405. This is a common clinical observation, as CGM captures hidden peaks and nighttime glucose fluctuations that discrete finger prick measurements often miss. Thus, the two methods serve complementary roles. Laboratory A1C reflects average metabolic load, A1C reflects dynamic system behavior. Both are valuable, but they operate at different layers of information. Conclusion: this study demonstrates that 3 independent glucose measurement methods converge to a consistent long-term trajectory over an 8-year period. If your data collection is over a short time period, you may not be able to observe this kind of longitudinal trajectory behavior. The high correlation among finger-based measurements, CGM data, and laboratory A1C confirms that 1. The underlying metabolic system is stable and measurable. 2. Measurement differences are minor and systematic. 3. Long-term glucose control can be reliably assessed using multiple methods. The method of measurement may differ, but the physiological truth remains the same. Most importantly, this work shows that long-term metabolic health is governed by sustained lifestyle behavior rather than measurement technique. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.